We are starting on top. Oh, exactly. Hello, everyone, and welcome to our USACO January 2026 Contest Live Solution Session. I'm thrilled to see so many of you here today. Fresh off the excitement of the first USACO contest of the year, whether you're celebrating your breakthrough or analyzing where you can improve, you are in exactly the right place. My name is Stacy, and proud to present SCAM Academy as we're bringing you this live solution session. For those who may not know us, SCAM is a Silicon Valley-based institute dedicated to help middle and high school students master the art of competitive programming. As of 2025, 75 SCAM students have made it to Platinum, and an incredible 41 have been selected for either US or national Canada camps. So just last season, we had 40 students for each camp, and 3 SCAM students earned a spot on the US national team. Speaking of championships, today we have an absolute legend join us. Kamil Dabrowski is an ICPC World finalist, an IOI 2025 problem writer, and a coach who has guided multiple students to gold medals at both ICPC and IOI. His insights into competitive programming are as deep as they come, and we're incredibly fortunate to have him walk through today's contest problems across gold and platinum. So let's get ready for some brilliant problem solving, expert strategies, and the kind of insight that can only come from someone who's been at the absolute pinnacle of competitive programming. Let's give a huge welcome to Kamil or Errichto.
Yeah. Thank you, Stacy. Welcome, everybody. Is the meeting already recorded? Is it being recorded in Zoom, if we want that to happen? So please check that. I'm sharing my screen, so I hope you see the slide with a summary of problems in Gold division. I will wait maybe 1 or 2 minutes before I start discussing anything important, so that a few extra people would join. Yeah, today we are discussing gold problems. We'll try to do it in 1 hour. And in 60 minutes, I'll start discussing the platinum problems. The plan for that as well is 60 minutes. We'll see if I manage to do it in time. Yesterday, we did bronze and silver problems, so you can find that on YouTube channel of XCamp Academy. I will monitor the chat on Zoom and YouTube. And on Zoom, tell me out loud if you also have some question and I don't see it immediately in the chat. In Gold, we had 3 problems, and generally problems in USACO, at least nowadays, they are not necessarily sorted by difficulty. I think in every division this year, it was just sorted alphabetically. So you shouldn't assume that the first problem is the easiest. We had 3 tasks: cow traversals, milk buckets, and supervision. And the order of difficulty, I would say, was maybe the second problem is easiest. And then arguably, for me, it was like this: second problem easiest, then third, then the first one was most difficult. But I see how people can swap the first and third. Maybe for some people, immediately the first one is you see how to solve it, and it's only some implementation difficulty, versus the third one you can for some time not know how to finish it with good enough time complexity. So if you have some other opinions about the difficulty, you can write in the chat. But I will discuss problems in order. So I will go first, second, third, starting from cow traversals. Again, arguably the hardest problem. But maybe not that hard if you have experience with similar problems, including one problem from USACO 2025. I have it open somewhere here. What was that? Reachable pairs. So maybe let me immediately open it. USACO reachable pairs. This one from gold. Problem 2 from USACO 25 January contest. It's related, and it's not the first problem of such type. I will paste in the chat, but also you can search for the name. I pasted in the Zoom chat. Please, somebody copy it into the YouTube chat. But let's see this one. In cow traversals, so first the gold division problem, we have n cows. Each of them is pointing to some other cow, and they will try to go there usually, unless this cow has a party in its own place. Every party has a type of COW. I will from now on just assume that a letter is mapped into a number. So we have three numbers possible. We have party of one of three types. And if a cow has a party in its own place, she stays there. Otherwise, she follows direction of AI. We need to handle some updates of some party happening somewhere now, and it wasn't happening before. The party stays there unless otherwise changed. And we need to know how many cows will attend party of each of those three types. How many cows will go and eventually stop at party of type 2. So they will keep going until they find a party happening. First of all, when we say that a cow I goes to another cow AI, this has a name. It's called functional graph. Functional graph, and we can draw it. We can represent this thing as a graph where if I have some nodes, or maybe let's first not use numbers, there's no point. From one node there is an edge to another, and so on. And eventually there might be a cycle. So as you can see here, a cycle. And generally, especially in very hard problems, what we should think about is a cycles and directed trees pointing into it, like so. So this is how a functional graph generally looks like. Okay, there is a cycle. Let me mark it maybe here, directed cycle. And then there are trees, directed trees entering some nodes of the cycle. That's what functional graph is. Not always we need to have that deep of an understanding of this. And in this problem, I think you don't actually need to find those trees and cycles. It's possible to do it without it, but this is good understanding. And every connected component looks like this. So a functional graph means that every connected component is equal cycle and trees going into the cycle. Initially, there is no party happening. So the answer would be that no cow attends no party. If I don't know if that was grammatically reasonable. And now if some party is happening, like here there is party of type 1, then all the cows that are in this subtree, they are attending this party from now on. If this is hard for you to analyze and, for example, to go through a sample, then what might make sense when we have a tree or something more complicated is first to process the statement, to understand the statement, how it behaves, for a line. So if I just had a sequence of cows, each liking the next one, and let's say that at the end, the last cow likes itself. This is a self loop is possible here. Then if there is party somewhere of type 1, there is party somewhere else of type 3, then the answer is that type 1 party is attended by all those cows, type 3 party is attended by all those cows, and finally, the final cows here in the suffix attends no party. We can say that that's party of type 0. And if new party happens, so if new node gets some new party, let's say of type 2, but it could also be of type 1 or 3, then it breaks this part into two smaller parts, because now everybody here will attend the party of type 2, everybody here will attend the party of type 3. In general, you should have, in gold division, I think you already should have intuition that it's hard in graphs to process connected components or some parts of the graph breaking down into smaller parts that are given to us in queries. That's not easy to do. There are no standard or easy algorithms that can do it. So in particular, something like this has no simple or linear solution. You're given a graph, process a fact that some edge is broken, like because this is what is happening here. We break an edge, we break an edge, we break an edge, and we need to in some way update the sizes of connected components remaining. That's something we cannot do nicely in a graph. What are our choices to solve this problem then? First, something that I will not discuss, but solution one, complicated, is to understand that first, I think it's good to go through this sequence and think how you would solve this thing. And how I would solve it is, by the way, with a set or a map, where I would store positions of parties. If I know the order of nodes, and let's say we pretend that those are numbered from 1 to n, then when there is new party happening, then I can use lower bound to find the next party, the previous party, and I will know what was the number of cows that were attending one party a moment ago, and now it's broken into two smaller parts, so I can update the values. That's reasonable. Then you can apply this logic to one of the subtasks. I don't have it here at the bottom of statement, but there was subtask that it's a permutation. Every connected component is a cycle, so that's also doable with set. And if you want to now solve this for general case like this, so in particular trees, what you can do or how this behaves is that for each tree that enters a cycle, you need to process something like this. There is information that party is happening, let's say here. So you need to get the information about size of this subtree. That's relatively easy. So you say, oh, this thing has subtree of 10. You pre-computed that, easy. But now, if there is another party happening, let's say here, it has this subtree, then the number of cows that will go to this party is equal to this thing, the size of green subtree minus size of red subtree. That's already more tricky, especially because a lot of other smaller parties might be happening already. So from this range, a simple version would be from this range, you want to know the number of, from the subtree, you want to know the number of cows that are not attending any party right now. Actually, it's even more complicated because there might be a party happening here, let's say. So this even bigger subtree. And now when green is the place with new party, what you need to also detect that, okay, everybody here in this area, a moment ago, those cows were, again, this is the tree directed up. Look at this thing. The arrows point towards the root of the tree, and this is how cows follow until they see a party. Okay, so everybody from here, let's say from this highlighted place, they will keep going up to a parent until they see something. So now, a moment ago, without this green thing, everybody here went to the red party. Now they go to green. So I need to, in some way, detect what is the size here, number of cows that go above the green guy to the red guy, how many of them there are, I need to detect. I need to mark them that now they are going to the green party, and I need to update the answer for red and for green party. That's quite some work, but it is possible. I think heavy light decomposition might be useful, but I would not use it. So maybe optional heavy light decomposition, question mark. I wouldn't use it myself. I would use Euler-Tur tree and segment tree that can do something with ranges. And most likely a lot of things are happening with ranges, so I think lazy propagation cannot be avoided. Or maybe it can be avoided, but I think most solutions should have lazy propagation here. Euler-Tur tree is the algorithm that flattens the tree into a sequence. So now subtree becomes a range, and we can actually query or update ranges. Also, I'm going to... Okay. Now, I told you, this is a complicated solution. And I saw in Discord that some people did it this way. Well, good for you if you managed to get the full score, but it was a lot of work. What I will discuss in detail is second solution that is much simpler. And I already was telling you, oh, and even in this thing, I didn't tell you the details about cycles. So I said that there are trees. I told you what we should do on a tree, but we actually have a lot of trees and they go into a cycle and something happens on a cycle. So it is really a lot of implementation. I would guess that on average, it would be 259 lines of code. So my estimation, 250 lines, maybe more, depends on how much you think about it. Then second solution has a lot to do with what I said here, that as an experienced participant, as somebody in Gold, you should already by now know that breaking connected components into smaller parts is very difficult in graphs. But the opposite is easy. It's easy and it's solvable to merge connected components into bigger parts. And so whenever problem is equivalent to our queries breaking edges, disconnecting components, so making smaller parts, very often we should do things backwards. So we are going to solve the problem offline, which means we read all the queries and then we process them backwards. Go backwards. And as you go backwards, the connected components will merge into bigger parts. So we will use DSU, disjoint set union or find an union. Let's see how that works. Do I have... I'm looking at a piece of paper to see if there is a particular example that I want to draw. Okay, let's see. Let's say that there is some small cycle. Looks like this. And maybe at least this node. There are some other nodes that are entering it. That might be enough for now. And we go backwards. It's not necessary in implementation, but it is possible to assume that at the end, everybody has a party. So you can read all the Q queries, and you can add n fake queries. Each of them is saying that every cow has some extra party at the end. It doesn't modify the answer for those queries here, because if you think about what the statement represents, it says you need to go through Q queries one by one and at every time say what is happening in total. The fact that you add some extra queries at the end doesn't change anything. So for convenience, if I didn't worry too much about the constant factor, I would add n queries at the end, one for each node, saying there is a party of the first type happening there. Because of that, as I go backwards for those queries, I can assume at the very end, everybody has a party. So maybe let me copy this graph, if this is technically possible. Okay. And before that happens, I might want to maybe mark nodes. So it would be easier for you to see. Okay. Now let me make a copy. And what happens at the end is everybody attends their own party. So the graph actually looks like this. Everything is its own connected component. So for example, this is a party of size 1. This is a party of size 1. We now go backwards. And let's say that I will for a moment assume that all of those are normal queries. So I will not do something special for those n. Actually, the only thing special that you need to do for those is not output the answer at the end. You need to save answers, but then Going forward, only output answers for those real queries. Let's say that there is party of type 3 happening here in this node. And this node is here in my right drawing. If now we say that this party is not happening anymore, and now I need to say there is no party here, then it means that the cow from this node will go to its parent. So that means that those two nodes merge. If a moment ago those two cows had some number from 1 to 3 describing the party that they were attending, now what I need to do is merge those two. So those two I merge into one connected component, and I forget about this party. I need to decrease the answer of type 3 by 1 and increase the answer of the party of type 1 by 1. So in particular, what I maintain is this, an array of size 4, where at indices 1 to 3, I maintain the answer of how many cows are attending party of each type. So now this is one connected component. Let's say that later maybe some other two nodes merged, maybe those two nodes merged, and they have a type 2. Let's see what happens. So this corresponds, by the way, to erasing few nodes like so. Okay, let's see now what happens if I keep going backwards and something tells me, yeah, in this suffix that I went through already, this thing had a party, but now it doesn't anymore. So I remove this guy. So it means I need to process its edge to a parent, so this thing. So those two nodes I need to connect into one connected component. Let's look at our graph that we maintain as we go backwards. So this is the graph from the input, and this is the graph that we maintain going backwards. This is the DSU graph. I need to merge those two things. So I tell DSU, merge the connected components or groups of those two nodes. And in part, the type of the party that stays is the type of the parent. So in the merge function, I have the merge function of DSU looking like this. And here the order is important. For example, I can always first provide child and then parent. And what happens is the type of the party where group X appears, we need to decrease the answer for this type. And for type of this party, we increase the answer. Okay, so I ask DSU what is the root, the representant of this group. I ask about its type. Its type happens to be 1. So I decrease the answer of 1 by something. I then erase that. And I connect those two groups. I mean, it doesn't even need to be this edge. DSU will not necessarily connect those two with an edge, right? But in some way, it will connect those two things into one connected component. So long story short, now this is connected component of size 4 and the party type 2. For every connected component, other than standard stuff for DSU, you certainly need to maintain size, where some DSU implementations don't do that, and you need to remember the party type. So those two things. The party type also can be 0, which happens if, let's see when this starts happening. Well, intuitively, the party is of type 0, so no party. If we go forever in a cycle without a party. And as we process things backwards, the moment it will happen is when the last item from a cycle is cancelled, the last party in a cycle. You might think that because of that, we need to detect cycles. Actually, that's not the case. As we keep processing the updates going backwards, the cycle will close automatically, and in the DSU, what will happen is that this is the moment when we try to combine two things from the same connected component. Right? Because each of those, look at this drawing on the left, the input graph. If every node appears once as losing a party as we go backwards, then every directed edge will be processed once. And in this thing, every edge, it combines two new things, except for the last edge of a cycle automatically. So in the merge function, what you want to do is usually we start like this, get parent of x, y is get parent of y. And now if x is equal to y, then we are finishing a cycle. So change type of this connected component or party of this connected component into 0 and then return. Otherwise, we do the standard merging thing where we combine two things. And this means this cycle a moment ago, and maybe some parts that were connected to this cycle, they had some party a moment ago as we process backwards, and now it doesn't have any party anymore. So I just decrease the answer of 1, 2, or 3 by the size of this connected component, and that's it. And I change the party type into 0. And what else? Finally, in the input, a node might have multiple parties of different type. So if in the input it tells you node 5 at time equal to 3, it has parties of type 2, then at time equal to 10, it has party of type 3, and time 15, it has party of type 2 again, and so on. As you process things backwards, keep in mind that all of those events, they are not erasing a party, only changing the type. So when each of those things happens, then you know that only you need to look up the connected component of this node and change the party, so also modify the answer. But only from the input, the first occurrence of a node, or as we process backwards, the last occurrence of a node, only then this is actually erase, which triggers the merge. So only at this thing you merge, at those things you only modify. Uh, and that's it. The time complexity, q plus n times log. It might be even smaller log because DSU has sometimes log star instead of log, or maybe log log. I don't even remember, some small logarithm. So that's the easy solution. And it's something very common. Whenever you realize that it's a graph where edges disappear and you need to maintain info about connected components, you should immediately think this. I want to do it offline, backwards, with DSU or something similar. Tell me if you have any questions. Mm, 27 minutes. I'm looking at the time to see if we'll manage to do gold problems in 1 hour, but I think so. For me, it was the hardest problem. Don't know about you. Party 0, I see a question about party of 0. I'm guessing either you are asking about party equal to 0 or about answer of 0. So let me tell you two things. Answer of 1, 2, 3 are things that we will output. Answer of 0 is something that we never touch and we can ignore it. Or even if you modify it, you never output it. But with this, you could track number of cows that don't go to any party. And regarding the type that we store for a connected component, so for every connected component here in the drawing with red, I showed you the type of a party. But as we process backwards, eventually a cycle closes. So then we can here maintain party equal to 0, meaning that those cows, they do not attend party of type 1, 2, 3. They keep going forever in a cycle. So that's what party equals 0 means. What do we have next? Milk buckets, arguably the easiest problem. And again, I have a similar problem for you. Pyramid array. CSCS.fi pyramid array. Yeah. What was Alan? What is that? Strange. Okay, this is the link I wanted. So here you go. Again, please, if somebody can copy paste it into YouTube, the link. The links that I paste in the Zoom chat, I think it's good if they will be on YouTube as well. That's a similar problem if you want to look it up later. Did I also have another one? Yeah, USACO haircut. So I have even one more. USACO haircut. And one more similar to milk buckets. What do we have? We have a sequence of values AI. And first we swap it around a little bit. And then we can keep doing the following. We take two neighboring elements, AI and AI plus 1, and we replace them with their average. We need to minimize the number of swaps so that we could maximize the final number remaining. For example, if my sequence was, let's say, 3, 1, 10, if what I should do is take two adjacent elements and replace with average. So what I can do is this. Take 1 and 3, replace with average. I will have then 2 and 10. I now take the two adjacent elements, 12. I do the average 6. So I'm left with 6. That's one possibility. Another is that I start by averaging 1 and 10. That will give me 3 and 5.5. Then those two I average. 4.25 is my final number. I want to maximize. I maximize the final value, so this is better. This is better. But I can do one more thing first. I can swap things around. So for the cost of one coin, I could, instead of this, start from, for example, this thing. Or I could start from, because a single swap of two adjacent elements is enough to obtain this. Or with two swaps, I could achieve 10 at the beginning. And with one more swap, I could even do this, which is the reverse of the initial sequence, which is very stupid because for sure, for the reverse, the final answer must be the same. Before we think what swaps are optimal, let's try to understand what intuitively makes sense if you want to maximize the final amount. So I have a sequence, maybe a long one, and I keep replacing two numbers with average. What it means is that whether those numbers were small and big or maybe too medium, it averages out and it kind of cancels. It matters less for the final value. So let's say that we have, for example, array with 1, 1, 1, 1, 9, 9, 1, 1, 1, 1. Taking those two nines and averaging into a 9 is a waste because we want to leave big numbers for the end. Perfectly, at the very end, we want to average two nines, which is impossible. So instead, intuitively, first I want to get rid of a lot of ones, get rid of a lot of ones. Perfectly, I would even average those two ones into a single one. So I will do some swaps to achieve that. And because if not, then what I can do is average those into 5 and then either this thing or this thing. I think I prefer to have a bigger number at the end. So I would average those into 5 and those into 5. But if instead I was allowed to swap earlier, I would swap in such a way that 1 is here, those two average to 1, those two average to 5, those two average to 7. That's better. So yeah, the big numbers I want to leave at the end. I don't want big numbers to be surrounded with small numbers. I want small numbers to be in order. And one possible idea you might have because of that is that we should just sort the sequence. So maybe it's optimal to always, if you start from, I don't know, this sequence, then sort 1, 2, 4, 7, 9, and average in order 1 and 2, then the result with 4, the result with 7, the result with 9. Turns out that doing it this way, and you can analyze few examples, or you can even implement brute force to verify that. This is optimal indeed. Or maybe it maximizes final value indeed, but possibly it uses too many swaps. It might use too many swaps because in particular, I can have in the input decreasing sequence. So from that, you might get a fix. I want to consider that the sequence should be sorted increasingly or decreasingly, and I wonder how many swaps are needed. That's also not correct, and my first sequence actually is a counterexample. This turns out to be optimal sequence because in the first move you want to average out 1 and 3, and whether it's in this order or it's in this order, it doesn't matter. The same operation of averaging is possible. What actually is important is that the big numbers are not surrounded with small numbers. In particular, the biggest number, the maximum from the sequence, should be at the end or at the start of the sequence. And then the remaining n-1 numbers, we will average out, and then we will merge that with the big number. And what is true for those n-1 numbers? The same thing. So, in general, I want among all the numbers their maximum to be at the start or at the end. This is the first maximum in the sequence. Then among remaining, the second maximum also needs to be at the start or at the end. Then for those, again, maximum at the start or at the end, and so on. For example, if we consider the numbers from 1 to 9, one possible optimal sequence after the swaps, is it 9? I think so, is maybe 9, 8, 7, 6, 5, 4, 3, 2, 1. This is optimal in terms of the final value you will get from averaging out elements. And the way to do it is 1 take with 2, you compute the average of 1.5, then you merge that with 3, you merge that with 4, with 5, with 6, and so on. It's a reverse pyramid. If you draw that, the index versus the value AI, you want it to be of this shape, bitonic shape, bitonic. Decreasing and then increasing, reverse pyramid. All right, but it's not obvious which part exactly should be in the decreasing part versus increasing part. In the input, we are given a sequence, and we want to swap things around. The task is certainly easier if it would be easier if numbers were distinct. If numbers in the input were distinct, then we can find in the sequence the maximum, and we can say that it goes to the beginning or to the end, because it doesn't matter where it goes exactly, we can say that it goes to the closer position. So the algorithm should locate the maximum, see its distance to the start or to the end, and say that it goes there. For example, this maximum is closer to the start. So how many swaps are needed? 3. The distance is 3, so answer plus equal 3. Maximum goes to the beginning. And you continue the process here. It's not easy to move things around in a structure, but there are data structures for that. But instead of finding the maximum and literally moving it somewhere, what you want to do is then pretend that it's not here anymore. A standard trick is for every number, write value 1 in a separate array. And when you take a number aside and it's not there anymore, put a 0 there. And then if you have some other number, let's say you figure out that the second maximum is here, then to know how many swaps are necessary to move it to the left, or how many are needed to move it to the right, you compute the number of ones on the left and number of ones on the right. because we're counting the number of swaps to sort sequence or double sort it, it's very similar, by the way, similar to inversions. If you read about different algorithms of counting inversions in a sequence, one of them is this thing. And in order to know the sum of values in a range, you can use segment tree. Okay, so summary of solution, if numbers were distinct, is that you take the input sequence, you find the maximum, or for example, you can sort numbers decreasingly, but keep information about the index for each of them. So you can sort pairs value comma index. Starting from the maximum, you see where it is, at what index it is. You ask about the number of remaining numbers on the left and on the right. So the sum on the left and on the right. You ask segment tree for that. And the minimum of them, you add to the answer. And this position you change from 1 to 0. So this is a sequence of basically Boolean values of whether a number is remaining or not. What you're doing equivalently is this. For every element AI, you're counting smaller elements on left and right, and minimum of those two counts you add to the answer. For example, if in the sequence we have 2, 7, 10, 20, 5, 8, 3, if we look at value, let's say 10, then as we process things from the maximum, 20 will be first marked as taken out, and it will be already somewhere else, so it will be a 0 actually. For 10, we will count that on the left there are 2 smaller values, on the right 3 smaller values. 2 is smaller, so it's cheaper for us to do swaps to the left, to put 10 at the beginning. So the answer is we increase by 2 when we consider the value of 10. This is how many swaps 10 needs to perform with smaller elements. Finally, we need to handle equal values. What happens if there is a sequence and there are few positions with value equal to maximum? Well, intuitively, some of them, it's cheaper for them or closer for them to get to the beginning of the sequence, and for some it's closer to the end of the sequence. And actually it's independent. I can say those 3 go to the left, those 2 go to the right, but actually for every element separately, I can decide how many smaller elements are on the left versus how many smaller are on the right. Smaller means remaining elements, so those that are still a 1 in the sequence maintained by segment tree. It's just important for such a 9 not to treat other 9s as smaller, because you don't need to swap with them. So the trick for that is, as we need to first sort elements from biggest to smallest, but for every element we need to process all its occurrences at the same time. So for value 9, let's say the maximum, I have a list of indices. Indices maybe 2, 4, 5, 8, 9. For each of those indices, I first tell the segment tree to change 1 into 0. And after that, after this all is updated for all the 5 elements, then the segment tree has a 1 only for strictly smaller values. And now for each of those 5 indices, I again ask segment tree, what is the sum on the left? What is the sum on the right? And I take the smaller of the 2 values. The way I think I implemented it is, I was very lazy. I think I did this thing to sort. So I iterate the input array and I say map of a of I pushback I. Map generally has bad constant factor, but if constraints aren't tight, then you can afford it. So I did this, and then I iterated the map. I actually iterated from smallest to biggest. So what I did is I started from segment tree of only zeros. I didn't need to initialize it to anything special. And as I kept from smallest to biggest, the segment tree automatically already has the information about smaller values. And what I did is I changed the zeros to ones slowly. And map is sorted by the value. So what I did here is, for the pair of int comma vector inside of map, I first iterate this vector, the indices. No, I first do the queries. For every I in the vector, query left, query right, answer plus equal min. And then for everything in the vector, I update, segment tree update, position I from 1 you change to 0. That's what you do. I can even for a second show my code, but I don't think it's anything special. What was the name of the problem? Milk buckets? Yeah, that's my code. It's quite neat. So if you want, you can, take a screenshot or later rewind the YouTube video to it. This is after we create empty segment tree, and this is the actual code, where for every pair of value, comma, the vector of indices, I iterate indices to ask for left and right sum. I increase the answer by minimum of the two, and then again I iterate indices, and each of them I update that segment tree. I do +1. I didn't even copy paste any segment tree code because the operations we need here are very basic. Yeah, so one part of training competitive programming is if you spend a lot of time to implement a solution or you struggled, it's very beneficial to look at codes of others, especially codes of people who solved it quickly. In Code Forces, for example, after the contest, if you struggled with a problem, look at the top of the leaderboard and open some codes and try to understand at least one of them that seems to be way shorter than yours. And yes, indeed, it's the same as CSES pyramid, as somebody is saying in the chat. And I already pasted in the chat the link to that. So once we figure out that this is optimal, it's the pyramid problem. Though in the pyramid problem, I think that we had distinct values. So here's some extra difficulty. Tell me if you have other questions. That was milk buckets. Then we'll move to supervision. We have a sequence or maybe line with people of two or cows of two types, coaches and campers. I think I will say coaches and students because it will be easier to hear what I'm saying. So we have a line. The students I will mark with just white. And the coaches I will use another color for. So coaches will be with this color. And there is also some range, the range D. Every student needs to be, there exists a coach within D units to the left. So student is happy if within D units to the left, there is at least one coach. Then it's a good situation. We need to count the number of subsets of people or subsets of cows that are good. That is, every student that goes is satisfied. So at least one coach is there in the input. I actually first misunderstood the statement. I thought that this range goes in two directions. That's what I implemented. It didn't work for the sample test, but turns out that the fix, once I realized the fix, it was few characters. Luckily for me. Okay. N is up to 1 million. I think there was subtask with n up to few thousand as well. So n squared allowed partial points. There was also stupid subtask with d equal to 0, but let's ignore that. And for our convenience, the values were distinct and already sorted. And that's it. Okay. When we have a line and some satisfaction condition about ranges, one possibility is to think this way. For a student, if I want to take it, then also I need to take at least one of those coaches. So there is some kind of implication. Sometimes this kind of graph-like analysis leads to solutions like 2SAT, but that's not the case here. It would be very slow, or it wouldn't work at all. Also, 2SAT cannot do counting. 2SAT can check if there is a solution. It cannot count usually. So that's not the way to go. What I can do is I can go and for every person decide if I take it or not. And after I kept making some decisions, I can remember something about those decisions to know if the next person can be taken or not. That can give you idea for inefficient solution. dp of I, the index in this sequence of people from left to right. And then what do I need to know for this next student to be taken or not? I need to know where is the previous coach, last coach. So it's n squared states. I can have this dp. What is the number of such possibilities or subsets being taken in the prefix up to index I, so that this would be index of the last coach taken. For every next person, if it's a coach and we take it, then we also replace this dimension. If it's a student, we can take only if the last coach position plus d is greater or equal than this position. And that's it. Very easy transitions. O of n squared time and memory will get partial points. Sadly, it's very hard to improve this because of the number of states. We already have constant transitions here per state, so yeah, this is not good. We need to have dp of I or dp of last coach. We cannot have time complexity better than the number of states in our dp. So that's not a good way to go. dp of I also, I think, is not good enough unless you maybe define it properly. That is, I don't think it's easy to phrase what we should represent dp of I for any arbitrary index I. Like it matters what was exactly the last coach taken. So when I was solving this problem, I went for dp of last coach. For every coach, I said, what is the number of solutions so far if I also take this coach? And this coach I know allows me to take the next few students. And then I can iterate. If this is the state, then I move to the next state. So I move to the next coach to be taken. So a quadratic solution, let's talk about solution in O of n memory, O of n squared time. Quadratic solution for every coach iterates what is the next coach taken. From I to j. And as I jump, I need to process students that are in a way. I know that coach allows me to take the next students within the distance of d and nothing more. So I can ask some separate data structure, maybe in logarithmic time, maybe in constant time, what is the number of students here? And whatever the count c is, the 2 at power c, 2 at power c is the number of ways I can choose students in between of ij. Also, I and j might be very close to each other. So if I transition from this I to this j, I only ask about the number of students within this range in between. So I transition from dp of I to dp of j. I and j are indices of coaches. And I do something like this, dp of I multiplied by power of 2 of something. Like this is a count. Count of students between of coaches I and j that are within range of coach I. Those are the transitions. And always when I finish, for every dp of I should consider possibility that this is the last coach. Then the answer should be increased by 2 at power the number of students here. Or alternatively, you can make some implementation trick. You can add a coach, one extra coach at infinity. Infinity should be far enough that the d distance is not enough for any student. And you say that the last coach taken needs to be this one. then the answer will be simply dp of that last guy, last fake coach. -1 because you don't want to count. The statement said we cannot count empty set. Though it depends on implementation if you will need this -1. If you have -1, be careful to use modulo properly. When you apply modulo operations, this doesn't work because it can give you negative value. Negative values don't modulo nicely in C++. You need to do it this way, to subtract 1. How much time we have? Not much. Okay. Now, to speed this up, I'm going to, this power of 2, I want to quickly sum up a lot of states. So for dp of I will transition to a lot of dp of j's, automatically telling them what power of 2 they should use. That is, if I have coach I here, then there is a distance of d here. I can just once, for the coach d, count the students that are here. Let's say there are 5 of them. And then all the j's that are in this range, all the j indices, should be increased by the same value. dp of j plus equal dp of I multiplied by power of 2, the 2 to the power 5. Very easy. Am I right? Am I saying something stupid? No, it's okay. Of course, with modulo operations. This kind of addition of a constant you can do using segment tree add or using prefix sums or running sums. What I did is running sums. That is, I only added the value at this position, at this index of a coach. Maybe I used lower bound, I don't remember, or you could use 2 pointers. So I find, for every I find the first coach that is after d units, and at that coach position, I increase it by this much, and I let running sums do the job. That is, as I keep going forward, this value will be propagated forward. So I actually here say running of j plus equal this, where j is the first index j after d units. And then as I keep going, always running of j plus equal running of j minus 1. Okay, that is how to handle transitions from I to far away j. The second type is that I need to handle transitions from I to j that is close, within the d distance. Then what is the formula? From dp of I to dp of j, I will transition, and I need to increase it by the number of students in between. And that depends on both I and j. But the nice way is to phrase it in terms of I and j, so that we could express it as a formula that splits into something dependent on I and j, and then we can optimize it, is that it's the number of students here. If for every coach you know the total number of students in the prefix up to it, so we define student prefix of I, number of students before coach I. With this definition, the number of students before I and j is easy. It's student prefix, or let me just say spref. Spref of j minus spref of I is the number of students in between. So 2 needs to be raised to this power. And if I need to say this, dp of I multiplied by 2 to the power of this, very common trick in harder problems, especially Platinum, and something to do with summation or even FFT, which is ICPC topic, is you get rid of brackets or you split into separately I and j indices. So this I will express as 2 to the power that divided by 2 to the power this, right? If you multiply something by times 2 at x minus y, equivalently you multiply by this and then you divide by 2 at power y. That's the same. So actually this becomes dp of j plus equal dp of I times power of 2 of S pref of j, and then divide by power of 2 of S pref of I. Yep, I will now group by index. So what I can do is when I'm at index I can compute this value, which depends only on index I. So given I can compute the highlighted value. It's a constant based on I. And for everything in this range, again, I can use segment tree or I can use running sums to add something in constant time to a range. To everything in this range, I tell it, I need to add to your DP this value multiplied by this value depending only on you. So to the range, I say I add this constant. It's like running sums number 2 of this range. This is pseudocode plus equal this thing. Here I use modular inverse. I can pre-compute inverses of 2. So this can be constant time here. I do this. But as I keep going, then for every future index, what I do is dp of I or dp of j, whatever, plus equal running 2 of I multiplied by this missing thing. So I know somebody earlier told me to increase myself by this constant, depending on that old value, multiplied by something depending on my current index. So when index 4 tells something to index 7, actually index 4 knows this value. So this yellow value is added to everything here. And when I get to index 7, I take this value that was added to me and I multiply it by this new value that I know now because it's based on me. Okay, that's how you can solve it. I will again show for a moment my code, but I will not go for it. And what was the name? Was it Supervision? Yes. 100 lines including the comments, so not that fast. I think that can be better, but you can look at this part, I guess. Yeah. Again, later you can rewind and study it more. What I did first is because I thought that coaches go in both ways, I actually changed every coach into a range. I numbered students by indices from 0 to the number of students minus 1. Every coach, I computed the range of student indices that is covered, and then I focused on those ranges. I forgot about positions of students and coaches. And then I have here something that is, you're given a lot of ranges, you need to compute how many subsets there are of ranges and then things inside of ranges. And here I transition between ranges, but it boils down to the same thing. I implemented in n squared multiplied, in O of n multiplied by lower bound. I don't know why this says n squared, some old piece of code. So it's n multiplied by lower bound. What's the similar problem score level on code forces that can practice? 2400? Maybe less than that. I'm not good at difficulties in code forces, maybe 2300. There is a website for that and you can look it up later, but it's not there right now. Codetiger.me. Codetiger.me. There is this website that estimates difficulties of USACO problems, so maybe in 1 month you will see the difficulty of that problem. 23 would be very hard gold problem. I wouldn't say that was that hard, so maybe 2000 plus a little bit. Anyway, you need to study DP counting problems, and you will encounter something like this. Any other questions? Yeah. I also had a bug which was related to, I think, some ranges being empty. So if you keep getting wrong answer, it might be because of that. Okay, so that's it for gold problems. We will start platinum in 1 minute or so. I will grab water. So I'm having a 1 minute break. And then we will go to harder problems. Let's go. Okay, 3 tasks. What was the order of difficulties first? I would say that, at least for me, P3 was easiest to start. So I immediately got some observations. Then it's implementation. But still, in my opinion, P3 is easiest. Then maybe it's P2 and P1. But I think people disagree heavily about it. I saw discussions in Discord, and every problem had some people saying that it's the easiest one. As I was saying yesterday a little bit for bronze and silver, your strategy should be not to focus on one problem because you don't know which one is the easiest. We will do them in order, starting from hoof, paper, scissors, triplets. Do I have similar problems? Yeah. So like before, I will show you some Euler mixtures. There are a few similar problems out there, including this one. Also including Baltic Olympiad mixture, which I think has the same problem, but it's hard. And there is also ICPC problem, 3 kinds of dice. CPC. No. So it's here the task C. I also know one problem from Polish ICPC stage. So generally, there are a lot of similar problems out there, especially in ICPC, and it is beneficial if you have solved at least one of them. If you did, then solving this is very reasonable. And if not, then solving this is very hard. I pasted into Zoom chat. Please somebody copy it into the YouTube chat if possible. We have a game of, let's say, rock, paper, scissors. Every player has some probability of playing rock, playing paper, playing scissors. For 2 players, we wonder which of them wins more likely with the other. And then we want to count triples such that first beats the second, second beats third, and third beats the first one. So for example, one person might have a probabilities of playing rock, paper, scissors 0.2, 0.45, and 0.35. This is rock, paper, scissors. Paper beats rock, rock beats scissors, scissors beat paper. And somebody else might have other probabilities. Let's just say that those are some values. Do I want to use A? Let's say X. X1, Y1, Z1. There is a second person with X2, Y2, Z2. And what is the probability that this person beats this person? say that this thing beats that thing. Probability x1 that first person plays this times this probability minus, or maybe that plus y1 times z2 plus z1 times x2. We compare this. This is probability that first person wins. We compare this with similar probability of when does second person win. X2 multiplied by y1 plus and so on. Something plus something. Already when you see this, you should think about geometry and cross product, but it's not quite there. If it was just simpler, comparing this to summation of two other parts here, it would likely be cross product, but it's not. It's the sum of more values. And I'm not even yet solving the problem about triples. I need to understand the logic of this, or the intuition behind this, how to equivalently nicely understand when one triple beats another. Now, there are different ways to proceed from here if you have not solved similar problems before. The first thing you can do is try to visualize, or use online tools for that. You can try to visualize the triples of points. Generally, when you get 3 points, sometimes it's three-dimensional geometry. So I will say here 3D geometry. This is not a good way to proceed. I'm just telling you a possibility. We know that the probabilities sum up to 1, so we know that they belong to some kind of triangle. And we are given a lot of points on this triangle, and we wonder what points beat some other points. In particular, we know that the point in the middle, there is this nice point 1/3, 1/3, 1/3, which in rock, paper, scissors, I think almost everybody knows, this is a balanced strategy that cannot be beaten by any other strategy. This thing ties with everything else. There is nothing else that can beat it on average or can lose it to it on average. Everything else in this triangle can be compared to each other, and mostly something is better than the other. Whatever is more towards rock will beat what is more towards scissors, roughly. So one possibility is to think about this triangle with the middle here, and if every vertex is rock, paper, scissors, you can roughly figure out that whatever is more towards scissors will beat whatever is more towards paper, and you will roughly figure out that this point beats whatever is in this area, and eventually from some math you will figure out the formulas required to solve the problem. But I think it's not very easy to do it this way. What I will do instead, again, but without knowledge of those other problems, is I will do the following observation. If my strategy of playing is, let's say, what did I use? 0.2, 0.45, 0.35, let's say, for rock, paper, scissors. If I try to compute my probability of beating somebody else, I claim the following interesting observation. If I decrease my probabilities by the same value, so I decrease everything by 0.1, then, and now the probabilities do not sum up to 1, so let's say that with probability 0.1 I play rock, with probability this I play paper, with this I play scissors, and otherwise there is a tie, or I don't do anything, whatever. Turns out that no matter how you define it, this is equally good strategy. Why is that? Because no matter what let's imagine that your opponent generates their random move first. And your opponent, you don't know about it, but they play paper. By how much you changed probability of winning when you modified your triple from this one to this one? Well, you decreased probability of rock, so losing by 0.1, and you increased probability, decreased probability of scissors by 0.1. So the win probability decreases by 0.1, loss probability decreases by 0.1, so the total is the same. Also, if you analyze this formula, where we multiply this thing by this one, but we subtract this thing by this one, you will see changing one triple down by 0.1 doesn't change the result of this comparison. I can go further with that. I can decrease everything by 0.2. So I claim that no matter what your exact math is, those formulas that we listed, the result of the math will be the same if I decrease everything by the minimum and I obtain a strategy that doesn't play rock at all. I claim that this strategy is equivalent to the strategy that plays paper with 25%, scissors with 15%, and it does nothing with 60%. Does nothing means there is a tie. Because that nothing strategy was equivalent to the 0.2 per each category probability, which is balanced. It's part of the balanced strategy of playing rock, paper, scissors, one of them at random. And now from 3 values, we are down to 2. If now in the input, every triple would have the same position as the minimum, like rock was the smallest of 3 numbers, we would be very happy already because we would simplify 3 numbers per triple into just pairs of values. Turns out I can go a step further, and the math still works if I decrease it more and I go into negative values. So I can, for example, subtract 0.35. So if I subtract 0.35, I will get this, and 0. I claim that this is still strategy that has the same results, if you do the math, against any other strategy. I subtracted the 0.35 per each category probability, which is a balanced strategy, so on average it ties. I can compare this with every other strategy. It doesn't matter that those probabilities in real life, they don't make sense. Formally, if it was a math problem and you tried to prove something this way, you would need to say that it's some kind of expected value of how much you bet. That I bet this much. So actually, I play rock with this negative probability. It's very strange to define it this way. We will not go there, but I think it's doable. Still, let's pretend that my probabilities are negative like this. So what I'm saying is for every pair, rock, paper, scissors, or every, triple, not pair, for every x, y, z, I transform this into x minus z, y minus z, and 0. And I focus on this, where nobody plays scissors. Nobody ever plays scissors. I just have a bunch of pairs of probability of playing rock, probability of playing paper. And now I want to count the number of like triples of competitors such that something. But for just 2 things, for just rock and paper, for just x1, y1, and x2, y2, just rock and paper, it's way easier to compute who wins on average. Probability x1 multiplied by y2, we compare against y1 times x2. So if I play rock, they play paper, let's say, and then paper wins versus the other combination. And if you put this to the left side of the equation, you have the cross product. So the solution here is that we first every triple transform into a pair like this, and then we can investigate cross products. And we have a lot of vectors, and vectors count triples of vectors such that something with cross product, which has very nice geometric interpretation of if you have those pairs, then one cross product is smaller than the other, or is smaller than 0 if one vector is to the left of the other. So for A, it wins against everybody here and loses against everybody here, which means we are counting triples of points such that B is to the left, to the right of this line, and C is to the left of this line, which roughly looks like this. One way to phrase it, count triangles where point 0, 0 is inside. Another way is count triangles such that they are on in one half plane of the 0, 0. And those are the bad triangles. So this means A wins with, here A is to the left of C, C is to the left of B. So A wins with C, wins with B, A wins with B. This is not a pair that you want to count, or not a triple. This is a triple that you want to count. In this top drawing, we have A smaller than B, smaller than C, smaller than A in terms of cross products. And for that, you need geometry knowledge. You need to know how to do it, and it's a quite standard task to do it. So also, I told you about this 3D. What we did here with simplifying triples is in some way equivalent to projecting points into the plane. We are looking at this plane containing this triangle, the plane x plus y plus z equals 0, and we are projecting every point into this plane, so we would only have two-dimensional problem, where this third point here becomes 0, 0. And then it's the same. But the easiest way is to just already be aware of the technique that we can do this transformation. That's what experienced competitors could do in this problem. Just skip all this logic, all this guessing or figuring out, and just know that this is what should be done. So finally, how to solve this geometric problem? You are given endpoints, x, y, count triples, A, B, C, such that in terms of cross products, we have this. The smaller means that cross product of A and B is negative. You can do that by sorting by angle and then using two pointers. And I still recommend that you instead count bad triples. So count such triples that, for example, A smaller than B smaller than C and A smaller than C. I would prefer to count those and then subtract from and choose 3. That's way easier. Count this and subtract. In all this logic, we need to be careful with collinear points as well. Collinear are always bad. So whenever we have a point here A and collinear point here B, those two strategies are equivalent. They are tying with each other. So this is a tie. Also, if it was on the other side, it would also be a tie. So such pair with anything else is a tie. We can count, I would count it maybe as a separate variable. So you want to take care of this. And also for every point A, you want to know how many points are in this half plane. If the number of such points is C, then for this point A, there are C choose 2 pairs of the points here, where each of them, with me, forms a bad triangle, a bad triple, such that this happens. Because, yeah, we can sort them. The 3 points that are in one half plane, we can sort by angle with respect from the point 0, 0. So we sort the points by angle. We use 2 pointers, because if points are in order, like 1, 2, 3, 4, 5, and so on, 8, 9, 10. When you get to point 2, you want to know the opposite point, like 8, because if you know that we have this angle, we have this angle here, that 8 is now, or maybe better, we have 2 and we have this 7 here. 7 is the last point that is in this same half plane as a 2. Then 7 minus 2 is 5. 5 is the number of points here. So 5 choose 2 is the number of your pairs that create bad triangles with 2. You just need to be careful with collinearity. So 7 should be the last point that gives you, let's say, strictly positive or strictly negative, sorry, cross product if you compare this versus that. And also, if there are a lot of here collinear points, you should process all of them at the same time. And you want for all of them to know how many points are here. And the number of them, for each of them, add to the answer this choose to. Not to the answer, to the number of bad triangles. Every bad triangle will be counted once, because it will be counted from the perspective of angle-wise first point. But be aware that here you also count triangles that look like this. There's this point, and then here two collinear things. You're counting those, which means in that implementation we need to be very careful. If I could spend 2 hours to maybe discuss all the Platinum problems, then we would discuss similar things. We would discuss maybe implementation, taking care of those collinear things. But we don't have that much time, so I will leave it like this. Time complexity is n log n. For somebody at Platinum level, I would expect that you can possibly not come up with this transformation, but once you get to 2D, you need to be able to solve this. Otherwise, you're lacking in geometry skills. Tell me if you have questions. If so, I will try to answer. Next will be a second problem, lineup counting queries. The same statement, but slightly different queries were also in bronze division. So if you didn't solve it, you can kind of say that you couldn't solve a bronze problem. Well, that one was a little bit easier. In that problem, you needed to answer queries of given time and the cow ID. You need to find its position, the current index in the sequence. That was one type of query. And also given time and position, you need to figure out the cow ID, the cow that is right now at this position. I think that that problem is not trivial, and it's a nice introduction to this one. But yeah, that's not what we're doing here. We have some process, and we need to, at some time, which is up to 10 to 18, count the given range of cow IDs, how many of them are in this range of positions. You can, if you want, later watch the analysis of bronze problems to see some extra stuff about this. Here, just in short, I will say this. We can implement a simulation. This was bronze, and it was, what was the name? No, so maybe that was in silver. Yes, sorry. Sorry that I told you that you couldn't solve bronze problem. It was silver problem. Yeah, we can run this and output some number of lines. This is hard to read, so I will save to a file. Open the file. Okay, I made my code so that the numbers would be nicely in columns. If something has only one digit, then I put extra space. Now, one thing you could do is look at a line, let's say some big line, this one, and you can try to observe a pattern. In this line, with numbers up to 34, numbers up to 17 are mixed up. Numbers from 18 up are nicely here. Then I see that number 17 is here, 16 is here, then 15, then 14, and the distance is 3. Then after that 11 is there, 10 is here, which seems to be 4 units to the left. But then from 10 to 9, we have more units because it's 5. So it's very irregular. It starts being ugly. That being said, I think it's true that among the remaining numbers, so if you ignore bigger numbers, then the distance will always be 3, I think. It's not exactly needed in the solution. At least there exists a solution that it doesn't use the fact, but I think that's the case, that you can here analyze this part and you can say the biggest. So in this first half of the 34 numbers, what you have is at some position 17. That's always second position from the right. Then 3 units later, you have 16. 3 units later, you have 15, and so on. And then when you're out of the sequence, you roll back here and you always skip, you go to the third available slot. So maybe if the 15 is, sorry, like 11 is here, then 1, 2, 3, 10 is here. So one possible approach is in this sequence, if always among a big number of slots, if you always take 1/3 of them, so you start from some big number, let's say from this one, and you process this from right to left, and you take every third slot, you're kind of multiplying this by 2/3, and the remaining number of slots is this much. If you process again, it will be this much, and this much, and so on. So after logarithmic number of steps, you will be left with 1 element or 0 elements. That logarithm is around 100 something, 100 plus a little bit. That's a logarithm of base 1.5 of 10 to the power 18. That's number of repetitions you need. And you can try to process that. I think it's a little bit similar to Josephus' problem. You will find it online or in CSES. I see some similarities. So I think that's one possible solution, to just now try to do some math with that and try to understand first with this every third element. If I want to take away every third element, how many cows of my allowed range are within the allowed range of positions? That might be ugly. I don't know. I didn't analyze this way. Instead, second possible solution, and that's what I will discuss, is if you look at this sequence and you look at a particular value, like let's say 6, you will see that for some time it stays in the same slot. Then it keeps moving to the left. Then it resets to the half of the sequence. Then it keeps going to the left. And then after getting to position 0, it again resets to the half of the sequence. I think we can better see it if we only output, let's say where number 6 is fine, where number 6 is. So let me run the program again and refresh the file. The 6 follows this nice pattern, very simple pattern, and the same happens for other problems. Sorry, for other numbers. So at time 6, the 6 is here at the end. At time 11, which is twice 6 minus 1, it's here. After 6 more steps, it is at the beginning, and at time 18, it resets to the half. Then, because it resets to the half, that's position 9. After 9 more steps, which is 27, we are at the beginning. And because of that, at 28, we are again in the middle of the sequence. So roughly, you can again say that this is time x, then this is roughly time x times 2 over 3 plus 1. Which means that whatever the initial number x is, it will be times 3 over 2, not 2 over 3. You need to multiply it by 1.5 at most logarithmic number of times, 100 something, before you run out of time, before you process all the 10 to the power 18 seconds. So lemma, every cow resets. The reset is from the beginning of the sequence to the middle, O of log times. And it's predictable / reliable where the cow is after every reset. And we can keep track of her. So if I focus on cow 6, I can figure out using after, let's say, 4 resets, I can compute where she will be in like 4 operations of multiplying by 1.5 with proper rounding up or down. So the task is that in some range, I want to figure out the number of cows of some values. So tracking a single cow doesn't do the job. But for every cow, it's very important. It's very important where she will be. And what I'm going to do is, because the number of resets affects the math heavily, I will iterate the number of resets that happens. My main idea for a solution will be for every number of resets from 0 to like 140, I want to here count such cows in ID range L1, R1 that they are in position range L2, R2 after time t, after exactly that many resets. Let's call this variable z, after z resets. Because the number of resets affects the math heavily, we can, given the number of resets, we can express where the cow is in terms of some formula, but rounding is annoying. Actually, maybe it's not a good idea to say that cow x, where she will be exactly after time t, again, because the rounding is annoying. So I think whether x is even or x is odd, it might affect what happens initially. So maybe I will look at it in a slightly different way, which again, if you solve the silver problem, you would know how to do it, because the silver problem consists of 2 parts. Analyze where the cow is, but also analyze for some position what cow is there. Because the alternative here is to do the following analysis. We can focus on some position, and we can, this position x, and we wonder what cow gets there, what cow is there. So whatever cow is there, she's also here, she's also here, she's also here, she's also here. And when we get to the middle of the sequence, we reset. So the cow apparently is here, then here, then here, then here, and here. And eventually we'll get to such position that we can say that she's here and it would be 4. I think the math here is not exactly right, because this is not the perfect middle of this sequence. But it's roughly like that. You can, for a cow, keep tracking back. And so given the time and position, in logarithmic time, we can figure out what cow it is. Then what I claim is that, maybe I will roll this back. I want the output with the big numbers. Refresh this file. Okay, thank you. The task says that we need to look at some time, at some position of indices. And for this position of indices, I want to figure out what cows are there. And as I told you already, we will iterate the number of resets, which basically means, again, maybe I will do some new lines. For this range, what I'm doing is I'm distinguishing few separate sequences that are very regular, and I'm counting them separately. For example, the cows that resetted 0 times, so they never got to the beginning, those are cows 16, 17, 18, 19, 20, and maybe 21. This is the every third position from the middle to the left. The big values, close to time over 2. But what is here after 1 reset? Those are cows, I'm guessing, 13, 12, 11. Okay, but how looking at the full array is supposed to help us with that? Assuming that something resets, let's say 0 times. Whoops, I don't know where I was. It's not good. sorry. Let's say that I was here. There is here this 16. There is here. Maybe I will increase the font. Oops. Okay, we are here. Where I'm investigating cows that resetted 0 times. If 0 times, then I can keep track. I can shoot straight up and right, get to the middle, and I will figure out what is the cow or the minimal cow that matches this description. For the math in your code, also it might be easier to shoot left and down. So from here, go there, and also you can look at the cow that is here. So after one more transition, she would be in the middle. That's the idea. Now, let's not look at numbers, let's look at the drawing. There is this pyramid of values. Let's also mark the middle. We get a query about some range. In a range, we need to count the number of cows that the ID is also in some range. First of all, this part to the right of the middle is trivial. This is very easy. Easy to compute because the cow there, the ID is equal to the position. Very easy to handle. We now only focus on the part that can be to the left from here. So let's say something arbitrary there. Let's say that I want to count cases of cows that resetted exactly twice. So I say the following. Whatever cow is here, I can shoot, whatever math is more convenient for you in code. You can shoot this way or you can shoot this way. And do the math from that. Or maybe, so if I'm here, then also I'm there. Here, how many resets I set? 2. So one more. Here, there. Okay. So there is here some cow ID. There is ID, or this row number. That is the cow that would get there. Sometimes this, what I'm doing as I keep going back is basically I'm dividing by 2/3. And sometimes this math will not be exact. I mean, we cannot exactly multiply by 2/3. We need to round. And because of that, my goal isn't exactly to compute the cow that gets here and is there after exactly 2 resets, because there might be no cow that is here after 2 resets. Maybe the cow here is after 1 reset or 3. What you're computing here is the smallest possible cow ID that satisfies that. So you want to know that for 2 resets, there is some range of cows, maybe from 8 to 10, that indeed get here. And your goal right now is to compute the value 8. You want to say that cows, for 2 resets, the cow ID needs to be at least 8. Similarly, you focus on this position and you do same math, and you will get some other limit, like cow smaller equal 10. And from that, you want to know, okay, so now you intersect this range with the range given in the input for the cow IDs, and you then will know that many cows might be here after exactly this many resets. And this, if we look here, is always equivalent to investigating one of those regular sequences. Like here, one of the regular sequences is 7, 8, 9. This is the sequence of cows here on the left that are here after 0 resets. For every such regular part, you compute the lower bound and upper bound in your range. To be honest, I did not implement this problem to verify the exact rounding of +1, -1. I have the convenience of being kind of retired from competitive programming, and I don't need to suffer from those off by ones. Again, in the USACO Discord server, I've already seen somebody pasting a nice code, so we can go there. I don't want to show it now because it's not my code, it's theirs. I didn't ask for permission, so just look it up. And as always in usaco.org website, eventually there will be code. But depending on what exactly you do, I think it's very easy to achieve the bed time complexity of, for every query you can do log logarithm times logarithm. If for every number of resets, you here also do another internal for loop that, for example, it multiplies by 2/3. It's not a great idea. You might get time limit exceeded. So what you want to do is realize that the operations of doing this for every number of resets, those are same operations. If from this left point of your range of positions, if you try to see where you are after 2 resets or where you are after 5 resets, you're doing the same thing. So what you should take is you should take this. I'm talking some implementation detail that affects both runtime and the convenience of your code. If at time t, you are here at position p, then equivalently I can say that after how many steps will you be there? After p extra steps. So this is t plus p, right? If this was 5 units to the right, then you need to go 5 extra units down to be here. So I claim that if this is t times plus p, then going here to the middle and going there, what this will be is t plus p multiplied by 2/3. What you want to pre-compute is your time from the query plus starting position allowed, which was L2, so t plus L2. You take this value, you multiply it by 2/3, 140 times, and you save this array and you use it. Same thing you need to do for this right endpoint. So also you need to do it for t plus L2, t plus R2. And I'm not sure if for t itself is needed. You can think about it. Homework, the details are homework for you, the viewer. I've seen in the code that they also use this. I'm not sure if it's necessary. Maybe it's redundant. Not sure. But once you computed that, you will, in constant time, for every range, for every number of resets, in constant time, you will get your bounds. So you can multiply this by 1, and then for sure it's accepted. Well, unless it's wrong answer because of some mistakes in math. Okay, that's the solution. You iterate the number of times the cow resets. And for every number of resets, you figure a possible range of cow IDs that has that many resets. Do you have any questions? If so, tell me. Even though I'm sure for many people the P1 was harder problem, for me, because I have a lot of geometry experience, for me P1 would be way easier to implement than P2, because in P2 there are so many ways you can mess up this rounding up or down. What I would do, and this is what I did in that silver problem, is I would look at the example of the pyramid created, and I would think for this example number, is it times 2/3 rounded up or down? Or maybe I need 2 plus 1. And I would just adjust the formula to make it for sure work for multiple values, and then it must be correct. Sometimes even I make a program that part of it is brute force, and I adjust some formula until the brute force agrees for the consecutive 1000 values. And then I say, okay, this is the correct formula. One more problem remaining, pluses and minuses. We have a grid where we fill it with pluses and minuses in such a way that no sum of consecutive segment, every sum is between -1 and +2. And yeah, a plus is +1, minus is -1. Before we see here what needs to be done, what needs to be counted, let's see then what is possible at all. Now, can I insert a table? Okay, I think this will be fine. So we have a table. I mean, we have a grid. If somewhere there is a plus, or maybe first this, a sequence, alternating plus and minus is correct and it doesn't contradict anything. If we have just plus and minus, plus and minus, plus and minus, then any kind of sum of a range will be close to zero. No matter what range you take, it will all cancel out except for maybe one element. So the sum will be 0 or +1 -1. Easy. There cannot be two minuses next to each other. So minus next to minus is not legal. Plus can be next to plus, but then the next element cannot be plus because that would be the sum of 3. We know that sum needs to be in range from -1 to +2. So this is invalid. After that, we need a minus. We never can have two consecutive minuses. So after minus, there needs to be a plus. There cannot be here another plus because if you have here +2 and +2 -1, that's a sum of 3, not valid. So if there are two consecutive pluses, then from now on in this row or in this column, everything alternates. It's plus minus, plus minus. Even more, let's look at surrounding of those two pluses. If I put obviously I cannot have two minuses there. What I can have is, I cannot, can I have this? Why not? Okay, this is invalid because after two pluses, there must be a minus next to it, and this is invalid. Okay, so I cannot here put two minuses, I cannot put two pluses. So it needs to be one plus, one minus. Let's say it's this way. Now, if I look at those two, or maybe because of this minus here, next to it, there needs to be a plus. And now with similar logic, because of those two pluses, here there needs to be a plus and minus. Oh, also here, two pluses already, so this needs to be a minus, minus. If you now look at this minus next to it, there needs to be a plus. And if you continue this kind of logic of what obviously needs to be there, which in head it's hard to figure out, but on paper you will rather quickly get it, you will get this double diagonal of pluses, which implies that everything else needs to simply alternate like so. And very often the full grid from now on looks like this. And from now on, just always it's pluses, minuses, pluses, minuses. I told you that after two pluses, in the same row, we cannot again have two pluses. So because of this, those rows are already decided. Also, those columns are already decided, but there is some remaining part. This part of the grid has no extra constraints on it, and I can do something special there as well. So just like here I created double diagonal of pluses, there also can be another double diagonal of pluses here. And it needs to look like this. Let me figure out the parity, because until there it needs to be minus, minus, plus. Can I have, so this is for sure. Here, yeah, I can have this. Minus, 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 and everything else just simply alternates. So what I created is this double diagonal of pluses here, double diagonal of pluses here, And it turns out that it's the most complicated thing that we can have in this problem. In particular, if there is some double diagonal anywhere of pluses, already it forbids anything fancy for all of this area and all of this area. We're always left with just some rectangle like so. And the only double diagonal that we can fit there, like it cannot be like this, because when we start a diagonal, it implies that it needs to continue. And here already we would have two pluses there, contradiction. So what I can have here is double diagonals here, somewhere in this corner. That's the most complicated thing we can have. We can have two diagonals such that they are disjoint in terms of rows and columns. We can also have a single diagonal. What already means is that answer is polynomial, not exponential. The answer, so the number of grids that are possible, because I can iterate the position of one diagonal, and either this is it, or I can iterate the position of second diagonal. So the answer is limited by something like number of rows or columns squared. The answer is of this magnitude. We don't need modulo. It will fit in long. The diagonals also might look like this, but then both will be this way. Great implementation advice is that you should run the algorithm once and then rotate the grid by 90 degrees, run algorithm again. So we will only focus on this kind of diagonals. The task says that we are given some cells that are particularly plus or minus, and we need to count the number of grids that match. So maybe we know that in some particular cell here, there needs to be exactly plus. And we don't know, maybe it's the part of normal part that is just plus, minus, plus, minus, plus, minus, or maybe it's part of double diagonal. That's the implementation task we need to solve. First of all, can I copy the table without the content? How does it look? Yes. I will focus on diagonals of this type. As I said, we run algo, then rotate everything by 90 degrees, then run algo. So I can only focus on this part. The very first thing that you should do is count the cases that have no diagonals. So consider that the plus is in the top left corner, check if everything is valid, if so, increase the answer by 1. Then put a minus in top left corner, check if everything is valid, it's just about parity. If so, increase the answer by 1. That was first phase. Then we assume that there is at least one diagonal, assume at least one diagonal, and we do this thing of run algorithm that we will now describe, rotate the grid, run algorithm again. I will only consider diagonals that look like this. Every diagonal, when you have a grid, the easiest way to number the diagonals is to count them, to say this is 0, this is 1, this is 2, this is 3, and so on. That is, a cell of row and column is diagonal number is equal row plus column. That's a well-known formula. If you are in cell 5,7, you're in diagonal number 12. Also, announcement is that this will take me like 5, maybe up to 10 more minutes. So we will not finish exactly at around hour. We will take a few minutes extra. And this is the last problem in Platinum. Okay, so we have this formula. Given cell, you know what diagonal it belongs to. And now what we have. I need to say that two diagonals, like for example, maybe 2 and 3, I consider marking with pluses. So sum two consecutive diagonals, there cannot be any minus there. Then from now on, everything needs to alternate. The fourth diagonal needs to be all minus. The fifth diagonal needs to be all plus. and so on, maybe until the end of the grid. For that, precomputation. So we have diagonals that go from 0 up to r plus c. I want Boolean arrays of for every diagonal, whether it can be plus and whether it can be minus. Can plus of r plus c plus 1 and can minus, or just make it two-dimensional. For each of possible type plus and minus, we want to know for every diagonal if it can be like that, or in the input there is some character that forbids us from choosing this type. Next, make a helper function can range given the bounds from L to R, some range of diagonal IDs, and initial parity, 0 or 1. Check if some range of diagonals, like 4 or 5, maybe until the end, the diagonals are counted up to there, whether it's allowed, we can alternate them like that, starting from this parity. This is 0 or 1, like plus or minus. And you want this constant time function, or logarithmic at most, to tell you, starting from here until the very end, can everything alternate, starting from minus? I would achieve that by using prefix sums, but it's not the only way. I can do, and it's like, the prefix sums depend on parity. Still, it's doable. In Olympiads, it's actually a good idea to start such helper function from a brute force. So make this linear first, iterate from diagonal L to R, and check if there is no contradiction. Always alternate parity, so change it when moving to next diagonal. Submit your code, see if it passes some tests and gets time limit exceeded. And once that happens, you just need to change it to faster data structure. Here, just simple array will be enough. Okay, so for every diagonal D, you check if D can be plus, D plus 1 can be plus. You check if range from 0 to D minus 1 can alternate. You check if range from D plus 2 to the end can alternate. And if so, you increase the answer by 1. And finally, the last step is that for every such pair of diagonals that can be plus, you can quite easily figure out until where it reaches, or actually what is the first diagonal, double diagonal, that we can use. In this case, this is already decided. This is already decided. The first place where you can have two pluses is here or here, whichever comes first. Let's figure this out. Oh, actually, that was the same place. Is that a coincidence? Yes, because it's a square. Usually for a rectangle, one of those two places happens first, like so. And so in this case, because it's wider than higher, the stronger limit is this. Okay, so this would be the first diagonal that has no contradiction with me. Also, parity must match. So whatever is the parity of this plus, it's the same parity as this first plus. So based on the R and C sizes of the grid and your D, you figure out what is the first available diagonal ID. And you're looking with your D and D plus 1, you're looking for such, let's call this E and E plus 1, diagonals E and E plus 1, such that D plus 1 and E have the same parity. E is greater or equal than some value that you get by doing something like row or column, dimension of the grid minus this. This is both can be pluses. From here until the end, everything can alternate. And also from D plus 1 to E, everything can alternate. And everything here can be done with prefix sums, or if you want segment tree, but that's an overkill. So as small precomputation, find all reasonable diagonals here, the second diagonals. So for every double diagonal, consider it to be the second one. Check if from here until the end it's good. If so, mark position E as possible. So do something like possible of E++, and then you know that diagonal E is a possible first part of this double diagonal. And then for D1, you can check how far we can alternate, which doesn't even require binary search. That can be separate array. It's easy to do it. How far we can alternate. This will give you some range of diagonals. And in this range, you're asking the count of this thing, so the sum of this, of some parity. You want D+1 and E to have the same parity. Again, that can be done with prefix sums. And that's it. That's how you count pairs of double diagonals. And for each, then you increase, for every such double diagonal D and D+1, you add it, to the answer, you add the number in some range that you found of the sum of possible, which you take from prefix sums. So it's a lot of prefix sums built on array of size r plus c. Or maybe 2 dimensions, 2 by r plus c, because it's separate for even, separate for odd. Time for questions. And that finishes the discussion of Platinum. We discussed 3 problems, the geometry one, the recursion and multiplication by 2 over 3, and the grid one with 2 double diagonals. A lot of implementation, but not a lot of data structures. No segment tree was needed today, which was, I think, unusual. If there are no questions, then I think we can wrap this up. Right? Should we say or announce anything else?
Yeah, Errichto, do you have any other suggestion to all the students or audience?
Well, I think, for example, this Platinum contest shows that knowledge of data structures maybe is not that important. So it's not that you need to know a lot of different theory, but practice is crazy important. A lot of times here for the Platinum, I showed you similar problems, something that is related. And it's not really a particular topic for a lot of them. It's just a problem that you needed to have encountered. So you need to solve a lot of problems and understand them. That's the most important thing. For Olympiad practice, if you want to be the best, you need to solve a lot of problems. You need to spend a lot of time problem solving. That's, I think, a takeaway.
Yes, yeah, that's pretty true. Because we hope that our student to do some contest summary and recap after the contest ends. This is also the suggestion from our teaching team. And this is the 4th year of SCAM to host a live solution after every contest ends. And this year we are pretty honored to have Errichto to help us to advance to the platinum level solution. So we hope the solution not only focus on the problem itself, but also some general similar experience and skills during the contest. So if you have any question, follow-up question and feedback, just feel free to let us know. And sincerely hope our live solution will benefit to more competitive programmers. Yeah, thank you, Kamil.
Yeah. Thank you, everybody, for attending. Have a nice rest of your day.
Thanks.
Bye, everybody.
I will stop the recording first.